Hello, this is a video on writing Lewis structures for molecules with double and triple bonds. In the last video, our bonds were all single bonds, so we stopped at number 4. Today, we're going to be looking at, if not, and the diagram has more electrons than in step 1, use double triple bonds to obtain the octet. What does that mean? You will learn shortly. I think the best way to do this is with an example. Well, today I'll go ahead and tell you, today is November 21st, Saturday. I'm recording this during the halftime of the OU-OSU Bedlam game. So if you watched that game, you might have noticed at the end of halftime or at the beginning of halftime, they kind of got in a little scuffle. So I'm gonna record this video, and then when I stop, I'll go back and edit the entire video while they're playing. So hopefully Tanner Schaefer from Canadian will get some playing time today. I think he's a fifth year senior, so I would like to see him play a little bit. Okay, otherwise, this is the video, and we're going to start with molecules: carbon monoxide, carbon dioxide, sulfur trioxide, nitrogen, and oxygen. And every year I'm amazed when I do Lewis structures because we will see, just by counting the electrons and drawing them and making the octet, we will predict that carbon monoxide, when you breathe it, will stick in your bloodstream, and carbon dioxide will not. And there's some cool things about nitrogen and oxygen, whether it's double or triple bonded, some interesting stories that I've read over the years. But let's start with number 1, carbon monoxide. First, let me go back to my notes. We're going to count the valence electrons. We're going to draw in this atom CNO, there's no central. Then we'll add single bonds. That will not work. Number 4. And then we'll add the double and triple bonds. Okay, here we go. So I'm going to pretend like I'm going to do single bonds, okay? Carbon has 4 valence electrons. Oxygen has 6 for a total of 10. So I'm going to act like a noob and say, okay, I'm going to draw single bonds around here, and then I'm going to make the octet for carbon, which is 3 lone pairs, and oxygen, which is also 3 lone pairs. So let me count them. 2, 4, 6, 8, 10, 12, 14. That doesn't match 10. So that Lewis structure's gone. Okay, let's try it again. I'll try a double bond this time. Okay, we'll try a double bond. So if there's a double bond on the CNO, each atom needs to have 4 other 2 lone pairs. Let me count those. 2, 4, 6, 8, 10, 12, which doesn't match 10. Okay, I guess I'll try a triple bond. Here we go. So there's C with 6 electrons shared between the C and the O with 1 lone pair. Okay, that's going to match. 2, 4, 6, 8, 10. Yay! So I'm going to redraw it without the circles. And that's the Lewis structure for carbon monoxide. Later, when we talk about VSEPR and bond shapes and angles and polarity, we will see that the oxygen is more electronegative. Therefore, there's a bond polarity toward the O. This little pointy sign is like the plus sign. That's the negative sign. And this predicts that just from counting electrons and looking at electronegativity, it predicts that carbon monoxide will be a polar molecule, which is what we see in real life. The higher the polarity, the higher the boiling point, the greater the intermolecular forces. It sticks well, and that's why carbon monoxide is a poison. When you breathe it, it goes in your oxygen, it dissolves in your blood, it goes to the hemoglobin, and it sticks in your hemoglobin, which I don't have a picture of that molecule right here. I may go find one and insert it, but it sticks somewhere in the iron part of hemoglobin, or some part of the hemoglobin molecule. I'll research it and look it up. But because it's polar, it sticks. And I've, unfortunately, here in Canadian Texas, I won't mention anything, but there's a town around here where a young man did have an accident where he was breathing in the fumes. It was an enclosed garage. They were running some kind of generator or some kind of machinery with an engine, and it was making carbon monoxide. So sad deal. Do not run a motor engine or something like that inside an enclosed area. Have a vent, have a ventilation. And I talk this with, I'll tell this little bitty story. A lot of older people have to watch out for their heaters because not every, typically, a lot of older people have a harder time. They don't maintain their house. They're not as wealthy sometimes as other people, and they just have like if they had a bad heater with a faulty uh, combustion area, there'd be carbon monoxide slip in, and they would be more susceptible to carbon monoxide poisoning from a bad heater, gas heater. Um, so now I think most houses have carbon monoxide detectors. That's kind of eliminates some of that problem. Okay, end of story. Number two. Now, why did I mention that? Because we're going to do carbon dioxide next, CO2. Carbon has 4 valence electrons, plus 2 oxygens have 6 each, for a total of 12, plus 4 is 16 electrons. Okay, let's draw this carbon in the central part of the molecule. And to begin with, I'll start with single bonds. That means carbon needs 2 lone pairs, and the oxygens each need 3 lone pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Too many. Well, I could do a double bond, and I would see it's 18. Then I could do a triple single, and that would be 16. But it'd be more symmetrical, and there'd be a greater advantage with formal charges. And some of you don't know what that is yet. Don't worry about it. If I do double bonds, so I'm just going to go ahead and jump to the double bonds, which means carbon has no lone pairs around it. And the oxygen will have 2 lone pairs around it. Let's count those. 2, 4, 6, 8, 10, 12, 14, 16. Yay, there we go. So carbon dioxide has 2 double bonds. And because the 2 O's are the same electronegativity, each bond is polar. However, the 2 dipoles cancel out because they're pulling in equal and opposite directions. Therefore, it's a nonpolar molecule. And when you breathe in carbon dioxide, which you do all the time, if you hyperventilate or breathe in a mask or something, especially during COVID, you're breathing in, because you're exhaling CO2, you're breathing it in back in your mask. But it's not as toxic because it's nonpolar. It doesn't stick in the hemoglobin molecules. Plus, maybe the bond length, carbon monoxide is closer, you'll see, to an oxygen O2 molecule than CO2 is. I'll have to research this, why CO is worse for you than CO2. That's just from my knowledge of living in being a chemistry teacher for 16 years. Okay, so there's number 2, CO2. Number 3 is SO2. And some of you are like, well, I'm just going to draw like CO2 because it's SO2. It's the same thing. Well, not exactly. And the reason it's not is because carbon had 4 valence electrons. Sulfur has 6, plus 2 times 6 is 12, plus 6 is 18 electrons. So when I draw the S, I can already tell from my CO2 that 16 and 18 are different. So I will draw. Let me pretend like I don't know what I'm doing. So there's my S with an O, and I'm going to draw a single bond. So I'll draw 2 lone pairs around the S and 3 lone pairs around the O, and that's not going to work. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 doesn't work, dude. Okay, well, let me try one double bond. If I do that, there are 3 electron pairs around the sulfur. I need a 4th is 1 lone pair. This O on the right will need 3 lone pairs. This O on the left will need 2 lone pairs to make it the octet. Excuse me for another dot. Let me go ahead and use my Apple Pencil to erase that bad boy. There we go. Okay, so there we go. I'll draw my 2 dots. 2, 4, 6, 8, 10, 12, 14, 16, 18. That works. So let me redraw it again. O, O, O-R-E-O. There was a commercial about Oreos in the past. So later we will see that that has 3 areas of charge density. If it was bonded, it'd be a trigonal planar, but because there's a lone pair, it's going to be bent at less than 120, maybe, let's say 115. So I'm going to put bent at 115, sp2 hybrid, and we'll talk about all that stuff later. This is just for, I'm just riffing on it. Okay, so let's do SO4, sulfur trioxide, SO3. So sulfur has 6 valence electrons. Each oxygen has 6. There's 3 of them. 18 plus 6 is 24 electrons. So again, let me act like I don't know what I'm doing, which I sometimes don't. And I'm going to act like, well, I'm going to draw 3 single bonds and then a lone pair around the S, and then 3 lone pairs around the O's. So it'll look, if I draw it like this, it's wrong, but it would kind of look like the NH3 molecule trigonal pyramidal, but it's not, because if I count the electrons, there's 8, 8, 8 is 24, plus this one is 26. So again, my electron counts don't match. Well, I'm going to have 2 electrons different, so I'm going to add 1 double bond. So when I draw 1 double bond, it's all going to work. The sulfur has 2, 4, 6, 8. It's got a double, single, single, that's 8 electrons around it. It's octet. The O's over here need 3 lone pairs. The O on the right needs 2 lone pairs to make the octet. So 8 around the O, 8 more is around 16, 18, 20, 22, 24. Now I've got 24 electrons around here. So this one is the Lewis structure. And I'll talk about a resonance structure later. I would draw 3 identical. Let me simplify it here. I could draw sulfur with double bond on the, it's going to be a little too big. Okay, let me try it again. I can draw sulfur with a double bond on the right. Whoops. Okay, try this again. There we go. Sulfur with a double bond on the right here. On the upper left here, or sulfur with a double bond down below. Either way, it's got the same Lewis structure. It's like you're rotating in space 120, or the electron could exist on one of the O's. There's a probability of 1/3, so there's 3 resonance structures for sulfur trioxide, and they're all identical. So molecule number 5 is nitrogen, and number 6 is oxygen. So let me write them down here so I don't have to scroll up again. Nitrogen is 2 times 5, which is 10. Okay, just like thought about that. The 2 ends are equal, and they will have a triple bond between them and a lone pair on the other side. Edit, edit, edit. Okay, there we go. So this nitrogen molecule is nonpolar. It has a triple bond, so it's a strong, very small bond, because double bonds are smaller, triple bonds are even smaller. Bond length is inversely proportional to bond strength. Okay, nonpolar, it's an sp hybrid because of the the double and triple bond. There are 2 pi bonds inside this molecule, and then 1 sigma in between the end, plus some lone pairs. So we'll talk about 1 sigma bond. That's the triple bond, 2 pi's and 1 sigma. And some of you don't know what we're talking about, but some of you have. This is a review of Lewis structure, so you know something about sigma and pi bonds. And I may introduce another video later, but I've got links to those easier ones. Okay, now that's over with. So nitrogen is a triple bond. The oxygen, 2 times 6 is 12. And again, like the CO2 molecule, if I draw an oxygen with a single bond, it's going to be 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14. Oxygen by itself will be 14 as a single bond, like F2. But if I draw a double bond between them, there'll be a double bond in between, 2 lone pairs on either O, and oxygen's a double bond. And if you look at the table, I'm going to have to insert this in a minute. The table of bond length and bond strength, you'll see a correlation. Nitrogen's a smaller bond. It's a stronger bond. It's got a higher bond energy, and it's a smaller bond length. So that's all predicted by just counting the 2 times 6 and 2 times 5. I mean, that's amazing. This has amazing predictive power, which it makes me feel very confident about all the stuff we learned about quantum mechanics and electron configurations and S&P orbitals. Okay, this is going to be an sp2 hybrid because we have 1 pi bond and 1 sigma bond. So we'll have that. Where's that other p orbital? Oh, it's in there. It's being used as the pi bond in molecular orbital theory. So it's also nonpolar. It's got 1 sigma, 1 pi. It's an sp2 hybrid. So all this stuff predicts the Lewis structures. Just by counting electrons, looking on the periodic table and valence electrons, it predicts a lot of stuff about, okay, sulfur dioxide. Sorry, I erased it, but sulfur dioxide is polar, sulfur trioxide is nonpolar, and polarity and nonpolarity have predictive power on bond strengths and intermolecular forces and solubility. So we'll talk about like dissolves like. A nonpolar molecule doesn't dissolve very well, not dissolve much in a polar substance such as water. So that's why oxygen dissolved in water, fish have got to have gills to breathe underwater. They don't breathe very well. Humans don't breathe very well underwater. Our lungs are not designed by evolution and nature or God to breathe very well underwater, unless you're an X-Men or something and got superpowers like Aquaman. DC Comics, sorry, not Marvel Universe, DC Universe. But we'll talk more about polarity and intermolecular forces and how they affect the ideal gas law. And there's a lot of predictive power just in this stuff about polarity that we'll see later on in the year. Okay, I need to remember to talk about the bond length, bond strength, edit, bond length, bond strength, so I can insert that table. Okay, thank you.
For these double and triple bonds. Sorry, here we go. Get the photo booth working again. Okay, so I've made carbon monoxide. We had 4 plus 6 electron is 10. To make 10 electrons fit around here with the octet, you have to have 3 bonds in between the C and the O. 2, 4, 6, 8, 10. Triple bond makes it work. So carbon monoxide is a very hard molecule to break. That triple bond is 3 times stronger than a regular CO bond. We'll see later on when we talk about bond strengths. And depends on if you're a Chem 1 student or an AP Chem student, you'll know a little bit more. Sorry, sick that working. Well, you'll know a little bit deeper what they're talking about here. Okay, carbon dioxide. To make it work, you have 2 times 6, which is 12, plus 4 is 16. To make the 16 electrons fit, you need 2 double bonds, which has 2 lone pairs on the 2 O's. It kind of looks like the oxygen double bonded molecule. Okay, sulfur dioxide. What I like about this one is when you put a double bond, there's 2 ways to put the double bond. Therefore, we have 2 ways to draw the molecule. Double bond over here or double bond over here. So it can be on the left or it can be on the right. Therefore, they draw a line in between them called a resonance structure. Resonance in physics means something else. It means like when waves vibrate at a natural frequency of something and it either destroys it, like the Tacoma Narrows Bridge or whatever else. For some reason, someone picked the word resonance in chemistry to indicate you have 2 or 3 identical Lewis structures, and you can think of it several ways. Number 1, imagine if you had molecules saying, I have to follow these Lewis structures. Then you click a picture, and one molecule would be on the double bond on the left, one molecule would be double bond on the right. Another way to think of it is, hey, I can rotate it it's got one mirror image plane, so there's 2 resonance structures, one over here, one over here. A third way to think of it is say, hey, the electrons exist in these orbitals, and there's a probability of where the electron exists. So there's a 50% probability the electron exists on the left, exists on the right. It's really a mix of them all. So there are two resonance structures for sulfur dioxide. Because sulfur trioxide has 3 identical oxygens, it can be on 1, 2, or 3. And rather than draw all 3 of them here, just imagine there's a double bond up here, double bond down here, and a double bond over here. So there are 3 resonance structures. Because this is for my Chem 1 people, we are not going to talk about formal charge and how to draw equivalent Lewis structures, different resonance structures, and pick the one that's best according to formal charge, with the electrons assigned and available, and there's a formula we won't get into in Chem 1. Okay, nitrogen is a triple bond. It looks just like CO, except because CO had different electronegativities, it's polar. Nitrogen is not. And that's a bad thing for carbon monoxide. Because carbon monoxide is polar, it has more intermolecular forces. So when you breathe in carbon monoxide and it goes into your hemoglobin, it sticks in your hemoglobin and it's really hard to come out. In fact, I read somewhere that the only treatment for carbon monoxide poisoning is just have a bunch of people breathing pure oxygen. And you may say, well, that's poisonous. Well, not if you're already poisoned. So there's like 10, 100,000, a million oxygens waiting to get in. And when a carbon monoxide does pop out, it's populated with oxygen. So then the person can finally start to breathe. And here's the double bonded oxygen. It's got 2 bonds and 2 lone pairs. And we'll talk more about these kind of things. And because oxygen is a double bond and nitrogen is a triple bond, it predicts a couple of things. Number one, it's easier to break the OO double bond than breaking the NN triple bond. So in combustion in your car, everyone has air in their car. You don't have a container of oxygen in your car. It just sucks in the air, and there's a filter, and it filters it out, and it meets the combustion chamber. If you have a carburetor, it mixes in there. If you have fuel injectors, it mixes in there. And the oxygen breaks more than the nitrogen. However, some nitrogen does break, and it makes NO compounds. They call it NOx, like nitrogen, oxygen, and then an X down there. And I'll have a clip of that in a moment. But they call them NOx because the X could be 1, 1.5, 2, whatever. So this is a little video of the oxygen double bond and triple bond. Now you try these molecules. Number 1, C2H4 was kind of like ethane, except it's going to be ethene. Number 2, C2H2 is going to be called, its real IUPAC name is ethyne. It's an alkyne. So it takes all kinds of people to do chemistry. This will be a double or triple bond. We'll have to find out in a moment. Number 3, Hcn Hydrocyanic Acid, or the Hcn molecule, hydrogen cyanide. Number 2, CH2O, either called methanol, it's an aldehyde, or formaldehyde. And I always hear people talking about, the dissections stink, man, it smells like formaldehyde. No, the new stuff is called formalin, and it's a synthetic. It's not an aldehyde, so it don't stink near as bad as it used to. And then number 5 is CH3COOH. And if you're a Chem 1, you're gonna see acetic acid later. We talked about the acetate ion, and in Chem 2, you've probably already done AP Chem. You've probably already done titrations. There's a good chance you did acetic acid. Well, like in Chem 1, at the end of the year, we try to find the percent acetic acid in vinegar. And I've got some videos about acid-base titrations. But there's more atoms here, so it's a little bit tougher. What you need to remember is this is a methyl group, CH3, hooked to a C, and you have to see what this functional group, this acid, this carboxylic acid, what does it look like? So draw the Lewis structure for it. It's a little bit tougher, but you can do it.